Alright, in this video we study improper integrals. So far, when we deal with an integral such as this one, something like dx from a to b, and we assume that this interval from a to b is a closed interval. But in improper integrals, this interval may be semi-closed, such as this, not including a, or this, not including b, or not including both a or b. Or we may even deal with integrals from negative infinity to positive infinity. Okay, let's start. So we first consider a function that is continuous and defined on a semi-open interval from a to b, including a, but not including b. So suppose function looks like this, and it's defined between a, including a, and not including b. But we want to integrate over this interval. Okay, so here's how we do it. We first define a closed interval here. So let's say this is t, and then we integrate from a to t. And so we integrate from a to t, just like we have been doing, and then take the limit of t approaching b from the left. Okay, so this is the left limit. T approaching b from the left, so we write minus 0 here. So if this exists, then we define this as this integral from a to b. Okay, it's called an improper integral. And this limit may be also written as this. We take some positive value, epsilon, and move epsilon to 0 from the right. So epsilon is always positive. So b minus epsilon is somewhere here, right? So this, if epsilon approaches 0 from the right, so keeping epsilon positive and make it 0, then we have the same integral. So if this exists, then it's defined to be this integral. In a similar manner, we can define an integral on this semi-open interval. So here, this one is infinity, and this one, so we integrate from a to infinity. So this is defined as this integral. First, we integrate from a to t, so that is on this closed interval from a to t, including t, and then move t to positive infinity, right? So if this limit exists, so if this converges, then we define that to be equal to this improper integral. And of course, we can define an integral on other type of semi-open intervals, such as this, not including a, but including b. Of course, this is defined as this. Let's see, a to b, so this integral is defined as this limit, t going to a from the right, t to b and f of x dx. So this case, let's see, so not including a, but including b. So we first take this smaller closed interval from t to b, and then move this t to a from the right. So this is a right limit. So if this limit exists, this converges, then it's defined to be this improper integral from a to b. And also a function defined from negative infinity to some value b. And this one is also defined to be this. from negative infinity to b dx. So this is limit t going to negative infinity and integral from t to b. Okay, so if this exists, then it's defined to be this improper integral. Okay, let's see a few examples. First, consider this integral from 0 to 1 over square root of 1 minus x dx. As you can see, this integrand here, 1 over square root of 1 minus x, is undefined at x equal to 1, but that is included as here. So this is an improper integral if this integral exists at all. So let's try to calculate this integral. So if this exists, then it should be this limit. Let's say we use epsilon here, epsilon going to 0 from the right, and integrate from 0 to 1 minus epsilon of this function. Okay, and that is equal to, let's see, that is equal to, so this is square root of 2 in the denominator, so it should be negative 2, I think, and 1 minus x, and from 0 to 1 minus epsilon, and so if we put this in x, then we get negative 2 square root of epsilon, and minus plus 0, that's 2. Okay, so if we take this limit, then this becomes 0, so it's 2. So this is so this does converge. So this improper integral's value becomes 2. All right, next example is this exponential of negative x. Integrating this from 0 to positive infinity. So this is obviously an improper integral because this one is infinity. So we can consider this as this limit, t going to infinity, and the integral from 0 to t. And let's integrate it, and we have limit, and this one exponential. So it's negative exponential of x from 0 to t. Okay, so this is limit infinity and negative exponential of negative t minus, so it's plus, and that's 1. Okay, so if we take t to infinity, then this one converges to 0, so this is equal to 1. So this integral, improper integral, becomes 1. Let's visualize this integral. So exponential of negative x, it looks like this. So we're integrating from 0 to infinity, so let's consider only positive x here. So starting from here, when x is equal to 0, this function takes the value of 1. And as x increases, this function monotonically decreases. So it becomes smaller and smaller, but it becomes never 0, but it converges to 0. So this integral means this area, right? So x going from 0 to infinity. It looks like, this area is like infinitely large, but it isn't. It converges to this value. So the area of this area under this curve is equal to 1. Next, consider a similarly behaving function. So integrate 1 over x from not 0, but 1 to infinity, let's say. Okay, so limit t going to infinity, and let's integrate from 1 to t, 1 over x dx. And that is limit t and log x. So this is natural logarithm from 1 to t, and limit and log t and minus log 1. Log 1 is 0, so this is just 0. And logarithmic function monotonically increases. So it's a monotone increasing function, so this diverges to positive infinity. Now look at the graph of this one. Okay, so this function looks like this. Okay, so when x is equal to 1, it takes the value of 1. So what this integral means is this area under the curve from x equal to 1 to x going to infinity. So this area looks much like this one for exponential function. So this is 1 over x. But in this case, this area diverges to positive infinity. And okay, again, consider this. Okay, next one is an exercise. Consider this integral 1 over x, again 1 over x, but from 0 to 1. Okay, so using the same figure, now we want to calculate this area. Okay, and you should show that this is also infinity, so it diverges. Actually, this result can be obtained by symmetry. This red area is symmetric if you make a mirror image. So this part is should be equal. Okay, wait a minute. This part should be, well, almost equal to this part, right? Okay, it should be equal to this part. But okay, this part is just finite. So if this part diverges, then this part also diverges. So just adding some constant here, constant part to an infinity, that's still infinity. So you can guess this should be infinity, but just by applying the definition of improper integrals, try to show this. Okay, next let's consider integrating on an open interval such as this from a to b, not including a and not including b. Okay, in this case, this improper integral. So we assume f of x is a continuous function on this open interval. Then we split this open interval into two parts. That is from a to c, and including c, and from c to b, including c. So we can split this integral into this and c to b. And now we have defined how to compute this improper integral and this improper integral. And if both integrals converge, then we define this sum as this improper integral on an open interval. And similarly, integrating for entire real numbers, that is from negative infinity to positive infinity. So some such integrals as this one, f of x integrating from negative infinity to positive infinity. This is defined as this. Negative infinity to some constant c and c to positive infinity. Okay, and if both improper integrals exist, then their sum defines this left-hand side. If they these integrals do not exist, then this left-hand side integral on the left-hand side doesn't exist either. By the way, we have this c here or here, and this c can be any value between a and b, or negative infinity and positive infinity, because they will just disappear anyway. So we can just pick any convenient value for this c. Okay, let's see an example. Let's integrate this function. 1 over square root of 1 minus x squared from negative 1 to 1. So at both plus minus 1, this integrand is undefined because the denominator becomes 0. So to calculate this, we do the following. We first, let's split this into negative 1 to 0 and 0 to 1. Then we calculate each improper integral separately. So the first one becomes something like this, from negative 1 plus epsilon and to 0, and limit epsilon going from the positive side to 0 and 0 to 1 minus epsilon. Okay, now we know the antiderivative of this function, so that is arc sine, limit, and arc sine x from negative 1 plus epsilon to 0, and limit epsilon going to 0 from the right, not this one, and arc sine x 0, 1 minus epsilon. And by the way, this epsilon and this epsilon, they are independent. So, they are not the same epsilons, okay? We happen to use the same symbol, but they are completely different things. Okay. So arc sine 0 is 0, and arc sine negative 1. Okay, let's see. So arc sine 0 is 0, and we have negative arc sine negative 1 plus epsilon. And limit. And arc sine 0 is 0, and we have arc sine 1 minus epsilon. Now, this limit, arc sine negative 1 plus epsilon, when epsilon goes to, epsilon goes to 0, then we have arc sine negative 1, which is, so we have this negative sign, which is negative pi half. And arc sine, so this converges to arc sine 1, and arc sine 1 is positive pi half. So we have, as a result, pi. So the value of this improper integral is pi. So as we noted, this epsilon and this epsilon are completely different stuff. So it is wrong to calculate an improper integral on an open interval as this. So instead of, let's see, from a to b, let's say. So instead of splitting this into two parts, so from a to c and c to c to b, instead of this, don't do this. So limit epsilon going to 0 from the right, and this a plus epsilon and b minus epsilon of f of x. Okay, so that means this epsilon and this epsilon are the same epsilon. So we only use one epsilon here. And calculating the improper integral like this is wrong. It can give a different results than the correct definition. And the same applies to this integral from negative infinity to positive infinity. So instead of splitting like this from negative infinity to c and c to positive infinity, c is some arbitrary constant. and taking this, so replacing this t, and taking this t to infinity, negative infinity in this case, and take this t to positive infinity for this one. Okay, instead of this, don't do this. So limit of t going to infinity, positive infinity, and integrate from negative t to positive t. Okay, this is wrong. So in this case, this and this t, these t's are the same t, the same and one t, and going to infinity at the same rate. So if you calculate this improper integral in this way, sometimes you can get a wrong result. Okay, let's see a simple example. Let's integrate this simple function x from negative infinity to positive infinity. Okay, according to the original definition, the correct definition, this should be first split into these two improper integrals. Let's say for constant, we take 0 here. So in negative infinity to 0 and 0 to positive infinity. Okay. So this one becomes, okay, so this one becomes, let's see, 1 over 2 x squared from negative infinity to 0, and 1 over 2 x squared from 0 to positive infinity. So this one becomes 0 minus infinity, right? So this is negative infinity plus this is positive infinity, which is undefined. Okay, so the integral, this integral is undefined. However, if you calculate this same integral in this way, so this is questionable, limit t going to infinity and from negative t to positive t. What do you get? So this one, limit t going to infinity, we have 1 over 2x squared from negative t to positive t, and limit t going to infinity. So this is negative t squared minus negative t squared, which is 0. So the result becomes 0, which is clearly different from this one. So this is actually wrong. So far, we have been mostly dealing with continuous functions. That is, a continuous function on a closed interval is always integrable, and a continuous function on an open interval or a semi-open interval, they may be integrable sometimes. Those improper integrals may converge. Now we consider functions that are not necessarily continuous, but it can be continuous at finitely many points. So let's consider a function on an interval. It can be open or closed, but let's say closed. So we have a function, and it can be discontinuous at finitely many points. So let's say at this point, this point, this point, and so on. Let's say a1, a2, and so on, up to an. They may be discontinuous. So something like this, or this, and so on. So different values here and there. So they can be discontinuous at finitely many points. Now we consider integrating such a function. Okay, so we consider a closed interval between a and b, and let's say a1, a2, and so on up to an are discontinuous points. Okay, such that a1 is less than a2, which is less than a3, and so on. And an and b and a. Okay, and if we split this integral from a to b of a function f of x into subintervals, between subintervals, and in each interval the function is continuous. Okay, so a to a1 and a1 to a2 and so on, and an to b. Okay, so each of these integral is an improper integral because uh, we do not consider include these discontinuous points in the integral. Okay, and if all of these improper integrals converge, then we can define the sum of this integral as this integral over the entire interval from a to b. So in this case, we can say that this discontinuous function f of x with finitely many discontinuous points is integrable on this closed interval from a to b. Okay, let's see an example. Suppose we want to integrate this function, square root of absolute value of x from -1 to 1. Okay, and this integrand, 1 over square root of absolute value of x, is undefined at x equal to 0. So it is discontinuous at x equal to 0. So to calculate this integral, we first split this integral at the point of discontinuity. So that is from -1 to 0 and 0 to 1. Okay, and both of these integrals are improper integrals because it's undefined at x equal to 0. Right. So let's calculate each of these integrals. First, let's take this one. So this improper integral can be considered as this limit, epsilon going to 0 from the right and -1 and negative epsilon here. Okay, square root of -x of this. And so to calculate this one, the value of x is negative in this whole interval, so we can get rid of this absolute value symbol here. So according to the definition of the absolute value of a real number, this is negative x, right? Because x is negative, so absolute value of x is negative x, which is positive. Okay, so this can be readily integrated. And let's see, so we have negative sign here, so it should be -2 and square root of -1, right? -1, negative epsilon. So that is limit and -2 and square root of negative epsilon is epsilon, and +2 -1 is 1. So we have this, and if we move epsilon towards 0 from the right, then this converges to 0, and we have 2 here. Okay, so the first integral becomes 2. This is equal to 2. And what about the second integral? So this one is again an improper integral. So this should be considered as this, epsilon going to 0 from the right and epsilon to 1. And applying the definition of the absolute value of a real number, here in this interval from epsilon to 1, x is always positive, so we can just get rid of this absolute value of x as just x. Okay, and this is, so if we integrate this, it should be 2 square root of x. And from epsilon to 1, and this is limit. And that's 2 minus 2 square root of epsilon. So this one converges to 0, and we have 2 here. Okay, so this is equal to 2, and therefore we have this integral's value as 2 plus 2, which is 4. So far, we have been very lucky that all of the examples we have encountered so far were, you know, it was possible to calculate all those integrals explicitly. But oftentimes, we are not so lucky to get the integral explicitly calculated. But still, we want to evaluate the integral if the integral converges or not. Sometimes it diverges, sometimes it converges. We may not know the exact value of the converged value of an integral if it converges, but we may be able to tell if it converges or not. Okay, and that can be a very valuable information sometimes. So here is a very useful theorem to tell whether a function is integrable or not. Okay, so let's say we have two functions, f of x and g of x, which are continuous on a semi-open interval between a and b, not including a, but including b. And suppose the following two conditions are satisfied. One, for all x in the interval, we have the absolute value of f of x is less than or equal to g of x. And second condition, the improper integral of g from a to b, g of x from a to b converges. Then we can tell that this improper integral of f from a to b, f of x dx from a to b converges. So this means that even if we are not able to calculate this integral explicitly, if we know that these two conditions are satisfied, so we know that g of x converges, then we can tell that at least that this integral converges, so it doesn't diverge. By the way, this function g of x is called a dominating function of f of x because it dominates in this sense. Okay, it is always greater than or equal to the absolute value of f of x for all x in this interval. Okay, so let's prove this theorem. First, let us define two functions, f of t as the integral from t to b of f of x, and g of t as the integral from t to b of g of x. Okay, by condition 2, this one, so this one converges, limit of t going to a from the right, g of t, so this converges, so this limit exists. And since this function converges when t goes to a from the right, then by the Cauchy criterion, let's see, for any epsilon that is positive, there exists some delta that is positive, and for all, let's say, s and t in the interval between a and a plus delta, so this delta is this delta, the difference between g of s and g of t is less than epsilon. Okay, so this holds because this limit exists, and vice versa. Remember? Okay, maybe it's better to write t minus s for later purpose. Anyway, so now let's consider f of t minus f of s. So this is, so and the absolute value of this difference. And this difference is by the fundamental theorem of calculus. This becomes the integral from t to s of f of x dx. Now, this absolute value of integral is less than or equal to the integral of the absolute value of f of x. This is actually another type of the triangle inequality. Triangle inequality. Okay, if you remember, we define the integral as a sum of rectangles, right? So basically, this integral is a sum of many things. And the sum of the absolute value of sum is less than or equal to the sum of absolute values, right? That is the triangle inequality. So in essence, sum of a plus b is the absolute value of a plus b is less than or equal to the absolute value of a plus absolute value of b. So this sum corresponds to this integral. So the absolute value of integral is less than or equal to the sum, so integral of the absolute values. Okay, so this is just another way to say the triangle inequality. Anyway, so now we use the condition 1. Where is condition 1? Oh, this one. Okay, so the absolute value of f of x is dominated by g of x. So using that inequality, so this is less than or equal to the integral of g of x from t to s. But this is equal to the difference between g of t minus g of s, which is less than epsilon. Okay. So we can get the absolute value out here because from here we can say that this difference is between negative epsilon and positive epsilon. So in any case, this is less than epsilon. So that means this difference is less than epsilon. So again, by the Cauchy criterion, the limit t going to a from the right, f of t, so this limit exists. So we can say that this integral of f of x converges. Integral of this one, f of x converges. And we are done. Okay, so let's see an example. Let's consider this integral. Integrating sine x over square root of 1 minus x from, let's see, 0 to 1. So this is an improper integral because at x equal to 1, this integrand is undefined because the denominator becomes 0. So now, integrating this function is very hard. So now we resort to this theorem using the dominating function. So what could be a dominating function of this integrand? Remember, sine x is bounded between negative 1 and positive 1. So this function, sine x divided by square root of 1 minus x, is dominated by 1 over square root of 1 over x. And this function, 1 over square root of 1 minus x, is easier to integrate. So let's integrate it from 0 to 1, 1 over square root of 1 minus x. And in a previous example, we actually calculated this function, and the result is actually 2. So it is convergent. So this improper integral has a limit. It converges. Therefore, we can say that although we cannot calculate the exact value of this integral, we can say that it does converge to some value. Yeah, it doesn't diverge. We have a corollary to the previous theorem, and that is following. Is the following, and again, f and g be a continuous function on a semi-open interval from a to b, not including a but including b. And now assume three conditions. First, for all x in this interval, g of x is positive. And second, f of x over g of x is bounded on this interval. And three, the integral, this improper integral from a to b of g of x exists. Then this improper integral of f of x does exist. Actually, proving this corollary is very easy, actually. Let's see. So by the second condition, f of x over g of x is bounded. But first of all, from condition 1, g of x is positive. So this absolute value of f over g is equal to the absolute value of f over g of x. So g of x, we can get rid of absolute value sign. And since this is bounded, this is less than or equal to some constant. Okay, so therefore, the absolute value of f of x is dominated by m times g of x. So this is the dominating function. But since by this third condition, the integral of g of x exists, then of course that integral of g of x times m is also a constant. Therefore, this function of f of x has a value. So this improper integral exists. And we're done. Okay, let's see an application of this corollary. So suppose we have a function f of x it's a continuous function on this interval between a and b, semi-open interval a and b. And now, if there exists some real number that is less than 1, such that f of x times x minus a to the power of k is bounded, on this interval, and then this integral f of x from a to b converges. So this exists. So how is that? So in this case, let g of x be x minus a to the power of negative k. So that means this function here, f of x times x minus a to the power of k, becomes f of x divided by g of x, right? So we are assuming that this function is bounded. So this function is bounded on this interval. Now let's see if this function g of x is integrable. So integrate this function g of x from a to b, and that is a to b x minus a to the power of negative k. By the way, this is always positive, right? And this becomes, let's see, 1 over negative k plus 1, x minus a to the power of k, negative k plus 1 from a to b. And by assumption, we are assuming that k is less than 1. So negative k plus 1 is positive. So this is okay. We can safely divide that. And this becomes 1 over negative k plus 1, b minus a to the power of negative k plus 1. And if we substitute a, that's 0. So that's it. So this integral does exist. Therefore, this integral of f of x from a to b also exists. Although we don't know the value of this, but we do know that it exists. It doesn't diverge. Okay, that's all for this video. See you later.